Hello, my name is Jose Lopez, and I will be presenting you my Eggstronaut challenge. So the main objective for this whole entire project or challenge is to basically create a model of a Mars lander. It's not supposed to exceed 450 grams in weight. Only can be made out of pasta. It could be boiled. It could be raw pasta, whatever the case. Um, and basically gained some inspiration from background of some Mars landers that have successfully landed on Mars, and basically just design a model. Um, the other objective is to notice how trusses and the forces that act on trusses relate to one another. Since I am going to be making stuff out of pasta, it is important for me to understand how the forces will get transmitted into the actual pasta so that way I can figure out the best strategy to where the pasta does not break on impact. Um, it will also help me whenever it's preparing me for the dynamics course, because it is dealing with motion, whereas in statics for this project, it's just about stuff in just a stable condition, whereas dynamics is more of in motion. Um, it'll also help me relate back to mechanical design since I'm making stuff from scratch and I'm just making it from some external materials, and it'll um, also help me gain knowledge for my future career path, which is mechanical engineer. So a bit of background info. This whole entire image is basically some Mars landers that were either successful or unsuccessful towards their ventures on Mars. As you can see, the outer circle is the Mars landers that were unsuccessful towards their voyage on Mars, and those six landers in the center that are on Mars are the ones that were successful on their travel to Mars. And of course, I'm going to be pointing out three key Mars landers, which I had gained inspiration for my own entire project. So one of which is the Phoenix lander. It was created by the US. Its main goals were to understand the climate change on Mars and the planetary habilitation on ice boundaries. Onto the left, too, you can see the description of the Phoenix lander, as well as all of its parts and materials, what each function of the lander's purpose was, and all of those essentials. The launch mass was to 650 kilograms. That includes all of the accessories. The lander mass, however, which is the one that I'm creating basically, the Phoenix was 350 kilograms. The dimensions are as labeled, and the main power generation was for this was solar panels that were made out of gallium, two of which, one for the lander, um, and they were either made out of solar panels or solar ray panels. It was launched on August 4th, 2007. Um, that was normal and with no abnormalities. Right here is the Insight lander, um, created, of course, again by the US. It was known as the Geophysical Monitoring Station and was evaluated for concept of study when two students had actually created a prototype, something similar to this, and that's when it was under development for a concept study. And eventually that project was used, which is now called the Insight lander. As you can see on the slide, it did have a total mass cruise of 649 kilograms. and it has the corresponding mass for each particular part of the lander, and its dimensions were 6.0 meters by 1.56 meters by approximately somewhere between 0.83 to 1.08 meters. And the power generation, of course, is solar panels, just like the Phoenix. Last but not least, one of the other landers is the Viking 1. There was a Viking 1 and the Viking 2. The Viking 1 was made, again, by the US at NASA at the Jet Propulsion Laboratory. There were two main missions on there, one of which was to get geographical imaging of the planet Mars, and it was to also search for life forms on Mars as well. It was just made of they were only focusing on the surface material of Mars, so anything more than that was not really the Viking 1's purpose. That was for more development later on the line for other landers that landed on Mars. This one was just to mostly track the terrain of Mars and see what type of components and elements it was made out of. The weight was 3,530 kilograms, which was the lander, and lasted about a year and 2 months before losing contact. Mind you, this was around the 20th century, so this is actually pretty good for a lander that had landed on Mars. And as far as returning data to Earth, there was obviously only two ways. One, relaying link data to the orbiter and back, and the other one is a direct link to Earth. And yeah, that was the Viking 1. So now we have the background info. Now we're going to talk about the design requirements for this. So the main requirements are as follows on here. You didn't really need scissors on there. That's just what I had put because that's what I had used. You need hot glue, plastic bags, pasta, all your essentials. But most importantly, it has to withstand at least 1 meter of its descent, weigh no more than 450 kilograms, and have a length and width of the lander of no more than 300 millimeters by 300 millimeters. And of course, I cannot glue joints, or cannot glue members, only joints. So at the ends of the pasta are acceptable for gluing. Gluing in between the actual members is not acceptable. So in order for me to tackle this project, I had to think about some strategies. So in order for me to get the most efficient design and to where I can find a very top height ratio to a low weight ratio. So one of which, of course, is a tensile strength for the pasta and egg. I had noticed when doing research on this that the tensile strength for an egg, if you were to press down vertically from its top and bottom, is going to be extremely hard. Whereas if it's tilted on the side, it's obviously going to be easier because the tensile strength in the center or the edges are not as strong. So my main strategy for this was to focus all of the force onto the top and bottom part of the egg. As far as the pasta goes, it's really easy to break if it were a long strand of uncooked pasta. So my strategy as well was to go for a much smaller length of pasta. That way it's less likely to break whenever an incoming force is acted upon that pasta. Secondly, parachutes. Understanding that parachutes is very key because I can use that in this project. One of which I used was the image that you can see down there, which is where it has a circle at the top. That allows airflow to go through naturally instead of it having to get all of that air in the parachute, which makes it act like a brick wall. So having that natural airflow will definitely decrease the drag and allow the descent to be nice and smoother. Next thing is triangles being key for this whole entire project. most buildings, or almost all buildings, have triangles in it, which are very good for distributing the load of forces throughout a building or structure. So making sure that I incorporate as much triangles as possible is definitely going to be a very good strategy in order for my lander to be successful. Next up is layering pasta. Now I know what you're thinking. I had said that I cannot layer pasta, or I cannot glue in between members of it. I can only do joints, which is exactly what I had done for this. I had combined multiple pasta and layered them together and glued like about 4 pastas at that joint, and then glued it to other joints of it in order for me to get a whole lot of pasta onto each length of the actual lantern. This made sure that there was a whole lot more um, force that the lander can withstand in order for this whole entire project to be yet again successful. So here's one of my first sketches. I have the advantages and disadvantages linked below. This is one that I first came up with, which deals with triangles, as you can see at the base, and the plastic bag acting as the parachute, having the front, right, and top views of each. I also made a little note on there because of I needed to make adjustments when necessary. On that, I only included 1 pasta per each length, or each member. So I made adjustments when necessary in order for me to make a lander that was successful in the end. Sketch 2 has a similar concept, except instead of having to go for a more diagonal approach for the body, I went for a more spread out. If you fan out pasta, that's kind of like the idea that I was going for. Um, Having the egg entrapped around the fibers of the pasta that was fanned out all around it. Still going for that triangular shape, of course, because that's our main strategy. I have, again, the advantages and disadvantages for this particular sketch. And again, adjustments will always be necessarily needed if I would actually need to make adjustments. Last but not least, my third sketch. There are, of course, the advantages and disadvantages there as listed. For this one, I was going a bit more originality on there. Instead of having to do triangles, I thought having to do a hexagon as my inspiration and a rectangle on there. I wanted to incorporate triangles as far as the connecting joints that lead up to the actual egg in order to make it secure. But you'll see by the end of this that I didn't actually end up using this sketch at all. So this was my final design that I ended up using. Um, as you can see, I didn't go for a huge big structure like all my other sketches. I instead, at the end of the whole entire sketches, I said I wanted to use something more simple, less complicated, and just something that would weigh less, because although the other sketches would weigh less than 450 grams, I wanted to go for something a bit more lightweight than something that was a bit more heavy. And these are, of course, the different types of views of it, and a more zoomed in model of how I had glued each member of the lander. Here are the videos that prove for me descending the actual um, lander, and I will be linking these videos also down in the description below. Apparently when I tested this out, it wouldn't allow me to replay back the videos in the actual presentation, so I'm just going to link those below. And yeah, the left side, of course, having me measure the actual 1 meter length, and of course the design, as you can see, kind of right here, is successful. Okay. So last but not least, there's a secondary video. This is where me testing it at a 2-meter descent. Of course, I'll be linking this video also in the description below because it was not working when I had put it up on there the first time. So yeah. And then finally the results. So the result for the 1 meter, of course, it was successful. The Eggstronaut survived. Only the right leg was the only thing that had broke, and the rest just remained intact. Um, Meanwhile, for the 2nd meter drop, the egg did break, sadly. Eggy did die, but he served his purpose. He's in a better life now. Um, the Eggstronaut, of course, did not survive, but I had noticed that when it was dropping towards its descent, it landed straight on its front side, and again, because of the tensile strength of the egg, it had a really easy time to just break, so the egg, of course, just did not survive. Here are my calculations for the velocity for the 1 meter descent because it worked on there. That was my math calculation for the whole entire just velocity, the time that it took, 0.42 seconds, the acceleration of Earth's gravity, 9.81 meters per second squared, and the distance was just approximately 1 meter. And that's my calculated velocity before the impact onto the ground. I had planned on spreading out the forces across the model evenly and absorb the impact of the lander, and then the force goes around the egg on the other members. Um, that was my overall calculation on there. You can also notice that on the other slides, or on the other slide, that I had used plastic bags surrounding the egg. This is also to absorb some of the force as well, so that the egg does not break as easily. It provides a little bit of cushion. So yeah, this is my first calculation for the actual lander. This is where I was doing the dimensions of the actual lander and figuring out how I'm going to calculate how much force was put into each member. And yeah, these are just the dimensions. The force, as stipulated above, I had to transfer from grams to kilograms, of course, because the units were newtons, and newtons are in kilograms times meters per second squared. So I had to convert that properly, and then, of course, do the math on that. And that force right there, that 0.792648 newtons, is, of course, divided by 3 because there are 3 legs. So the force has to go evenly distributed on each 3 legs. So whenever you see that arrow pointing, that normal force is 0.264216 newtons per each leg of the actual lander. And this is my calculation for one of the legs of the lander. Since each 3 are pretty much identical, I had put a note on there saying that since it's all symmetric, all of the uh, members are pretty much equal to each other. And of course, you can see the math on there, summing each of the forces to 0 for the x and y dimension and solving it accordingly. And yeah. Now my overall performance. The performance was in drop height in meters per weight in grams. It only survived 1 meter, so I used the performance of just 1 meter. Since the egg did not survive the 2 meter fall, I just only put the 1 meter. And that was the performance, 0.012 1.37, which is approximately 1.237%. Um, in that number is compared to other models, of course, it's pretty low. The closer the number is to 100% defines a great model. Um, and note that the 80.8 grams is with all of the accessories that comes with the lander, all the plastic within that surrounds the egg, the actual plastic bag for the parachute, and etc. So final conclusions. So overall, the egg drop was successful. I was able to have my Eggstronaut survive at least 1 meter high. Sadly, the Eggstronaut did not survive any higher than 1 meter, which is overall fine. The objective was successful overall. Um, and there are definitely some parts of the project that I can improve on. For one, is the legs of the lander. Since only one right leg broke, that was either because of poor construction or the fact that I didn't have enough members together. I could definitely have improved on that. I had really enjoyed this whole entire project as a whole, and yeah, I can't wait to do something like this again in the future.